Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized pieces. Today, we're diving into the brain of an AI.
Not literally, of course, but we're looking at a paper that gets as close as you can. It's called Why Retrieval-Augmented Generation Fails, a Graph Perspective, and it tackles a really common frustration we all have with AI chatbots.
Right, you ask a chatbot, say ChatGPT or Gemini, a question. To make it smarter, we have these systems called RAG, which stands for Retrieval-Augmented Generation.
Let's break that down. Retrieval means the AI can look things up on the internet or in a specific database. Augmented generation means it uses that information to create or generate a better answer. It's like giving the AI an open book test.
Exactly. You'd think with the textbook right there, it would get a perfect score every time. But it doesn't. Sometimes, even with the correct information right in front of it, the AI still gives you a wrong or nonsensical answer.
And that's the mystery this paper tries to solve. Why does RAG fail? It's not enough to know that it failed. The researchers wanted to know how it failed. To do that, they decided to look inside the AI's reasoning process.
Most people treat these huge AI models like a black box. You put a question in one end, you get an answer out the other, and what happens in the middle is a mystery. But these researchers found a way to map out what's happening inside.
They used a technique to create something they call attribution graphs. You can think of it like creating a subway map of the AI's thought process. Each station is a piece of information, a word from your question, a fact from the retrieved document, or a word in the final answer.
And the subway lines connecting these stations show how information flows between them. A strong, busy line means two pieces of information are heavily influencing each other inside the model. By looking at the shape of this entire map, they could see what a good thought process looks like and what a bad one looks like.
And the differences were striking. When the AI got the answer right, the subway map was deep and complex. Information traveled a long way through many different layers of the model, connecting lots of different ideas. The flow of information was also really well distributed, like a busy city with many interconnected routes.
It's like a thoughtful student who reads the question, highlights key terms, cross-references several paragraphs in the textbook, and then synthesizes all of that into a coherent answer. It's a deep, deliberate process.
But when the AI got the answer wrong, the map looked completely different. It was shallow. The information didn't travel very far. It's like the AI took a major shortcut. The map was also fragmented, with lots of isolated stations that weren't connected to the main network.
And most interestingly, the information flow was overly concentrated. Instead of a balanced network, you'd see one or two stations hogging all the attention. The AI would get fixated on a single keyword or phrase from the document it found and ignore everything else.
This is like a student who panics, skims the book for a keyword that was in the question, finds the first sentence with that word, and just copies it down without understanding the context or whether it actually answers the question.
The researchers gave these two styles of thinking names. The good one is called question-constrained evidence grounding. It's a mouthful, but it just means the AI keeps the original question in mind the entire time, using it as a guide or a constraint to make sense of the retrieved evidence.
The bad one is called surface-aligned evidence grounding. This is when the AI just latches on to superficial similarities. It sees a word in the question that matches a word in the text, and it just assumes they're related without any deeper understanding. It gets distracted by things that look right on the surface.
So once they could tell the difference between these two thinking patterns, they did two really cool things with that knowledge. First, they built an error detector.
Right. Since the graph or map for a correct answer looks so different from an incorrect one, they trained another AI to just look at the map of the reasoning process and predict, is this answer going to be right or wrong? And it worked incredibly well, much better than just asking the original AI how confident it was.
But the second part is even more amazing. They didn't just diagnose the problem, they tried to fix it in real time. They performed a kind of gentle AI brain surgery.
They created what they call an intervention. While the AI is generating its answer, they gently nudge the flow of information. In the early stages, they tell it, hey, focus more on understanding the question itself before you get too distracted by that document you found.
And in the later stages, they'd remind it to keep referencing the question to make sure the answer it's building is still on track. They're basically encouraging the AI to use the good, question-constrained pattern of thinking.
And it worked. By reshaping the internal routing of information, they were able to reduce errors and improve the AI's accuracy, especially in tricky situations where the retrieved text contained both useful facts and distracting information.
So the big takeaway here is that for AI, it's not just about what information it has access to, but how it uses that information. Giving it a library card isn't enough. You also have to teach it how to be a good researcher.
And this graph-based approach gives us a powerful new window into the AI's mind, allowing us to understand, predict, and even correct its reasoning failures from the inside out.
It's a huge step toward making these powerful tools more reliable and trustworthy. That's all the time we have for today. Thanks for tuning in to Daily Papers.